Picture this. You're a physical chemist working in the 1930s. You have a firm grasp on many of the concepts that we've discussed thus far. The structure of the atom is coming into very clear focus thanks to the work of Dalton, Rutherford, Thomson, and Lewis. Their long since proposed theories about the constant struggle of those atoms to obtain valence octets explain the driving forces behind many forms of chemical bonds. But you aren't just any physical chemist. You're famed chemist Linus Pauling. A chemist so brilliant in the pursuit of science and so engaged in its beneficial and ethical applications that you're destined to win not one, but 2 Nobel Prizes in your lifetime. One in chemistry and one for peace. Now, Linus Pauling was an American-born chemist who spent his youth tinkering with reagents and perusing chemistry books in his father's pharmacy in Portland, Oregon. His interest took flight, and by about 1925, he had worked his way to a graduate degree from the California Institute of Technology. As a young man, he found himself in Germany, learning from such revered names as Bohr and Schrödinger. But the real connection which might have set Pauling's legacy was between him and an Englishman named Sir William Lawrence Bragg. As Pauling was trying to make a name for himself as a physical chemist, Sir William Lawrence Bragg had just developed an incredibly powerful technique for probing molecular structures with X-rays. This technique is called X-ray diffraction. X-ray diffraction allowed scientists for the first time to determine not only the identity and ratios of atoms making up molecules in a compound, but also their positions in those molecules. Molecules would finally begin to yield the secrets of the spatial arrangements of atoms within them, arrangements that make every one of them unique. Pauling quickly mastered the technique in his graduate school years at Caltech, measuring and cataloging the angles and lengths of chemical bonds to levels of accuracy that were previously unimaginable. And what Pauling found was that most long-used theoretical estimates of bond lengths and angles in the 1930s were simply wrong. The bonding theories of the day did not match his findings when he applied this new technology to old questions. So, in the middle of a prolific career unraveling the laws governing how chemical reactions take place, Pauling found himself contemplating a disconnect in our understanding at the most basic chemical level, that of bonding. He had to find a way to explain the discrepancy between the old and the new understanding of how molecules were put together. One of the fundamental questions with which Pauling was struggling was this. Take a molecule of methane gas, one of the simplest molecules known to exist, just one central carbon surrounded by 4 hydrogen atoms. Methane had been known for many decades, yet what Pauling observed about methane when he turned Bragg's new technology on it gave him pause. See, methane forms a perfect tetrahedral molecule. In this molecule, all 4 carbon-hydrogen bonds are identical, absolutely indistinguishable from one another. Every probe available to Pauling told him that methane has only one type of CH bond, all exactly the same. But the central carbon has 2 distinct types of valence electrons. Right? There should be 2 s electrons and 2 p electrons. Now, if covalent bonding were taking place by the overlap of atomic orbitals in carbon with the s orbitals of the hydrogen atoms, shouldn't there be 2 different types of CH bonds in methane? One resulting from the overlap of hydrogen's s orbital with a carbon s orbital, and another resulting from the overlap of a hydrogen s orbital with one of carbon's p orbitals. So Pauling was faced with a serious problem. Schrödinger's earlier work clearly showed that isolated carbon atoms should have 2 different types of valence electrons. Yet, VS-EPR theory properly predicted the tetrahedral geometry of methane with 4 perfectly equivalent bonds. The 2 theories weren't consistent with one another. So, what was going on here? Was one of these theories wrong? Or was there something more going on when atoms form bonds? Is there some sort of fundamental geometric change that atomic orbitals underwent when forming bonds that hold molecules together? Pauling wisely threw his hat in with the latter idea, suggesting that orbitals themselves could combine and change as bonding takes place in a process that he called hybridization. His idea was that when an atom bonds, its valence orbitals can combine to average out and form any number of identical orbitals needed for bonding. It was not only a stroke of genius, it also won Pauling his Nobel Prize in chemistry. Today we'll spend some time exploring how this elegantly simple concept helped to further bridge the gap between our understanding of the structure of atoms and the structure of molecules. Let's start by thinking about a very simple example, and we'll connect this to hybridization. I enjoy rum and cola as much as the next guy. Perhaps you'll join me, right? We'll have to make two. So that means I'm going to take a cup of cola and a cup of rum. Now, to make my drink, of course, I'm going to mix them. So I'll put them in a large container and mix them together. When I pour them out, how many cups do I get? I get the same number I put in, don't I? I get 2. But each of them now contains material that's 1/2 rum, 1/2 cola. If we had a third person there, we have another friend, let's put another cup of rum into the mix, right? If we do this, we now get 3 cups out, and each of those is only 1/3 cola and now 2/3 rum. And if we decide to really make it a party, have somebody else over, now we're going to need to make 4, right? So let's add yet another cup of our rum, right? Might be about time for us to think about calling in sick tomorrow morning. We'll blend that together. We now get 4 cups out, each of which is 1/4 cola, 3/4 rum. This principle is exactly the same way that the laws governing hybridization of orbitals will work. The hybridization of orbitals is not all that different than this process. Multiple atomic orbitals can be grouped, blended together, then divided into equal parts to create a new set of orbitals with new properties that are a sort of weighted average of all of those that went in. Take a closer look at the electronic structure of a carbon atom, something that we've done before, but this time, let's think about it in terms of energies. The valence shell of a carbon atom contains a 2s orbital and 3 2p orbitals. And carbon's ground state configuration, the lowest energy arrangement of electrons it can have, is 1s2, 2s2, 2p2. But remember that an orbital can only hold 2 electrons at most. So the 2s electron pair has to be separated in order to properly prepare our carbon atom to bond with 4 hydrogen atoms. In our energy diagram for a carbon atom's orbitals, we can clearly see that this means promoting an s electron up into a p orbital, which will require some energy input since 2p orbitals are higher in energy than 2s. Now, if the structure of orbitals on the central carbon atom did not change during the bonding process, we would expect to have 1 bond to hydrogen made through a carbon s orbital and 3 bonds to hydrogen through overlapping p orbitals. But Pauling's theory predicted that just like our rum and cola can produce equal servings that are identical in composition, for example, 1/4 cola and 3/4 rum if I had used such a recipe, atomic orbitals can do the exact same thing when bonding takes place. 1 s orbital and 3 p orbitals combine or hybridize to form 4 new orbitals that are each 1/4 s character and 3/4 p character. Now, as this takes place, their energies change slightly, becoming a bit higher in energy than an s orbital, but a bit lower in energy than a p orbital. This process doesn't only change their relative energies either. It also changes their shapes into something resembling a combination of s and p orbitals. A dumbbell, but one which is slightly elongated on one side and slightly smaller on the other. Now, it was these oddly shaped orbitals that allowed Pauling to finally explain methane's bonding. Now, before we get to looking at the structures that Pauling had proposed for methane, let's first take a look at those orbitals that are in its valence shell and think about their energies a little bit. So let's begin with an unhybridized carbon atom, which would be at the center of a methane molecule. Now, we already know that carbon's electron configuration is 1s2, 2s2, 2p2. Right? And so this would be a ground state configuration for an unhybridized carbon atom. Now, if that carbon atom wants to make 4 bonds, though, we have a problem, don't we? The problem is that the 2s is fully occupied. There's a pair of electrons there already. So how's it going to make a bond when it's already got a lone pair in that location? Well, the only way to fix this in an unhybridized atom is to take one of these 2s electrons and promote it into the 2p system. Now I have 4 unpaired electrons, and I'm ready for my carbon atom to make 4 bonds. Of course, the problem with this is that the 4 bonds aren't going to be identical to one another. There will be 3 bonds involving the 2p orbitals, but there will be a 4th bond that involves the 2s atomic orbital. Now, let's think about hybridization and how that changes the game. Let's say we have a carbon atom, but instead of having a 2s and 2p subshell, those 2 shells combine and hybridize. Right? So I'm making an orbital smoothie here. I'm mixing s and p orbitals, blending them up, and then reproportioning them out so that I have 4 sp3 hybrid orbitals. Now when I put the 6 electrons from my carbon atom into this system, notice that I not only have 4 available orbitals for bonding here, each with 1 electron from the carbon atom, but that they're all of exactly the same energy. So if Pauling were right, then methane in the hybridized state should have 4 identical bonds. Whereas in the unhybridized state, it's going to have a really messy looking structure because those are not all identical orbitals. And so by looking at the structures, it was very clear that Pauling had to have been right about hybridization. So let's think a little bit more about hybridization and not just carbon atoms. Any atom can hybridize, any atom at all. Now, second row elements, of course, are going to be doing this hybridizing with their valence shell, which is the second energy level. So we'll be dealing with s and p orbitals in the case of second row elements. But we don't necessarily have to have all of them hybridize. It's possible, for example, here to have, in our example on the left, just 2 hybrid orbitals and 2 remaining unhybridized p orbitals. And when we do this, because we put 1 s orbital and 1 p orbital into the hybrid system, we call this an sp hybridization state. We move 1 over, let's say that we take 3 hybrid orbitals, leaving 1 unhybridized p orbital behind. We call these sp2 orbitals, again, because we've mixed 1s and 2p orbitals to make the hybrid system. And finally, the one with which we're familiar, in which we have all 4 of those second energy level orbitals hybridized to form sp3, meaning 1s and 3p. Now, when we move on to third row elements, things get a little bit more complicated. Because, remember, third row elements have access to a d subshell. And d orbitals can hybridize just like s and p orbitals can. So, of course, a third row element can hybridize in much the same way that a second row element could, forming, for example, an sp hybrid system on the left here. Or it could form an sp2 system. And similarly, an sp3 system. Nothing different here. We're just using the third energy level instead of the second. But because the third energy level has these available d orbitals, we have to consider the possibility that they may participate as well in hybridization. That leads to 2 new potential hybridization states that are only available to elements in the third row and beyond. Those are sp3d, in which one of those d orbitals participates, and also over here, sp3d2, in which 2 of those d orbitals participate. Now, if you look closely, you'll notice that these numbers correspond to those electron domain geometries that we looked at earlier, right? There are 2, 3, 4, 5, or 6 hybrid orbitals, which are able to hold 2, 3, 4, 5, or 6 electron domains. So these 2 concepts are very intimately tied together. And this helps to explain why we can have expanded octets on third row elements and beyond. So the sp3d and sp3d2 hybridization states correspond to trigonal bipyramidal and octahedral electron domain geometries that we looked at last time. You may also notice that d orbitals, though they're all exactly of the same energy, are not of exactly the same shape, the way that p orbitals are. And this offers us an explanation for the unusual trigonal bipyramidal geometry that has 2 different sets of bond angles. So Pauling's tinkering hasn't just allowed us to unify our understanding of the atom with VSEPR theory, but it also cleans up a bit by addressing previously unanswered questions. So, we just learned how hybridization of atomic orbitals can allow central atoms and molecules to create a group of identical or nearly identical orbitals, all of which have some amount of S character. We saw how this model can account for the ability of single atoms like carbon to make many identical bonds to other atoms. But there's more to understand about hybridization. You might recall from our bonding discussion that sigma bonds form directly in between nuclei. Now, this means that in most cases, hybrid orbitals are good at forming sigma bonds since they have some s orbital character. Lone pairs, of course, aren't involved in bonding, but they prefer to be in the lowest possible energy state that they can, which, again, usually means being in a hybrid orbital. So sigma bonds and valence shell lone pairs tend to be found in hybrid orbitals. But pi bonds, those bonds that make up the second and third bonds in multiple bonds, behave differently. Recall that pi bonds form by the side-to-side overlap of unhybridized p orbitals. Because hybridization changes the shape of orbitals and makes them less symmetrical, hybrid orbitals can't form these kinds of pi bonds. So now that we understand the energetics behind hybrid orbital theory, we can more quickly determine the hybridization state of an atom simply by counting sigma bonds and lone pairs on the central atom. All right, so let's start tying structure to hybridization states in atoms. We're going to do this by looking at a few familiar compounds. We've looked at just about all of these, if not all of these, previously in the course. What we're going to do is use the Lewis structure of these compounds in order to determine their hybridization state. We're going to look at CO2, boron trifluoride, methane, phosphorus pentachloride, and xenon hexafluoride. Now, drawing their Lewis structures should be a snap for you because we've covered this already. And when I draw these Lewis structures, notice that I'm leaving out the lone pair electrons on the peripheral atoms. Now, the reason I'm doing this is that they are of no consequence to the hybridization state of the central atom. Okay, we're all done here. We've got our Lewis structures for CO2, BF3, CH4, PCl5, and ZeF6. Hybridization states of central atoms can be determined from two important pieces of information. How many sigma bonds are on there, and how many lone pairs does it have? We combine that information to determine hybridization states. Let me show you how. Let's take the example of CO2. In carbon dioxide, I have two electron domains here. Both of them are bonding. Now, that means that those first bonds there that I've highlighted in red are, in fact, sigma bonds. They go into hybrid orbitals. But the other bonds, right, the second bonds in those double bonds, are not in hybrid orbitals. They are in unhybridized p orbitals. So I have two sigma bonds there. Now, looking at BF3, I have 3 sigma bonds. Methane, I have 4. PCl5, of course, has 5, and xenon hexafluoride has 6. In this particular case, I've chosen all molecules that have no lone pair electrons on the central atom. So this makes the exercise even easier because there are 0 lone pairs on the central atoms. Meaning that I have, in CO2, I have 2 hybrid orbitals, and the recipe for 2 hybrid orbitals is sp. In boron trifluoride, I have 3 hybrid orbitals, and the recipe for 3 hybrid orbitals is always sp2. Carrying on, methane would be sp3 because of its 4 domains, PCl5 would be sp3d, and xenon hexafluoride, of course, would be sp3d2. So it's pretty simple when there are no lone pair electrons on the central atom. Now, when there are unpaired electrons on the central atom, it's not that much more complicated. All we have to do is draw the Lewis structure again, but remember to count those lone pair electrons on the central atom as a domain. So, in the case of SO2, sulfur dioxide, water, sulfur tetrafluoride, and xenon tetrafluoride, we see that all of our Lewis structures contain at least 1 lone pair on the central atom. So, let's count sigma bonds and lone pairs and use that inventory to determine the hybridization state. In the case of SO2, I have 2 sigma bonds, but I also have 1 lone pair. That's a grand total of 3 hybrid orbitals necessary to create that configuration, so I'm looking at an sp2 hybridized molecule. In the case of H2O, I have 2 sigma bonds and 2 lone pairs for a total of 4. 4 domains means sp3 hybridization. In the case of SF4, we're looking at 4 sigma bonds and 1 lone pair. Grand total of 5. Our recipe for 5 hybrid orbitals is always sp3d. And of course, for xenon tetrafluoride, we have 4 sigma bonds as well. But unlike sulfur tetrafluoride, we have 2 lone pairs now for a total of 6 domains or 6 hybrid orbitals. That would be an sp3d2 hybridization state for the central atom. Understanding hybridization of orbitals is a crucial underpinning to our understanding of molecular geometries. As we'll see again and again in this course, the shape of a molecule, the geometric arrangement of the atoms that make it up, can be every bit as influential in determining the properties of a compound as the identities of the elements making it up. The world is filled with examples of this. Take the example of the molecules making up ordinary gasoline. Among those compounds are molecules like octane and isooctane. Both are compounds with the molecular formula C8H18, but each combusts under very different conditions of pressure and temperature. In fact, the combustion properties of isooctane are so much better than those of octane that oil refiners build and run massive reactors containing expensive precious metal catalysts like platinum. They do this just to help convert octane into isooctane for better fuel blending. And all of this is possible because of the tetrahedral geometry of the sp3 hybridized carbon atoms in these molecules. They create a three-dimensional branching network that can take on very different shapes with just a few atoms. Another connection between hybridization states of atoms in your everyday life is the need for you to have phosphorus in your diet. The human body is made primarily of oxygen, carbon, hydrogen, and nitrogen. All of these elements hail from the first 2 rows of the periodic table, and so they don't have access to d orbitals to take on more complex hybridization states. But not much farther down the list are elements like sulfur, phosphorus. Now, phosphorus is a part of the glue that holds some of the most critical molecules in biochemistry together. Take the example of RNA, the chemical cousin of DNA, which, among other things, plays a role in converting information in our genes into useful molecules that our bodies rely on to function. Phosphorus holds individual nucleic acids together through a bond known as a phosphate ester. Phosphate esters are pretty tough, and they keep molecules like RNA and DNA intact fairly well. But when the time comes that your body needs to break down RNA to build new messenger molecules, it needs a way to break those bonds and disassemble the RNA. Nature's choice of phosphorus as a backbone atom was no accident. As the bond holding ribonucleic acids is broken, the phosphorus in the backbone has to change its hybridization state from sp3 to sp3d in order to allow this reaction to take place. Place a different atom there, even a chemical cousin like nitrogen from the same group, and the properties of that system would change so dramatically that it would be unusable in a living organism. Both fuels like octane and biopolymers like RNA are such complex, indispensable, and fascinating materials that they'll get a lot more attention later in the course. But for now, they offer shining examples of how the most fundamental theories like Pauling's hybridization theory can not only help us to understand these critical materials at the molecular level, but help us to design and produce new materials that offer the greatest benefit when put to use. So let's review what we've covered today. In this lecture, we endeavor to understand the apparent conflict between the electronic structure of individual atoms and those that are bonded to other atoms. We saw how legendary physical chemist Linus Pauling brought his intellect to bear on this problem, formulating a theory of orbital hybridization. We saw how, in second-row elements, this theory involves a given number of s and p atomic orbitals, combining and averaging to form the same number of hybrid orbitals, each with some s character and some p character. Next, we considered elements from row 3 and beyond, and how they have available d orbitals, which can also join the hybridization party, helping us to explain that odd shortcoming in Via's EPR theory when 5 electron domains are present. And finally, we took a look at a few chemical systems whose geometries are critical to their function. And we saw how orbital hybridization has allowed chemists to explain and predict the properties of naturally occurring and man-made molecules alike. Our investigation of chemical bonding is almost over. Soon, we will start to see not only how these bonds exist, but how they are broken and formed in chemical reactions. But before we can do that, we have one more important topic to cover. Molecular orbitals are our topic for next time. So let's put our understanding of hybridization of orbitals to the test with a challenge problem. Here's our problem. What are the hybridization states of the central atoms in the following compounds? BRF5, SCl4, and SO3. Now, in order to answer this question, we're going to have to dig a little deeper back into the course and bring back our understanding of Lewis structures because they'll be critical to getting the correct answer. Now remember, when we do Lewis structures, we always place the least electronegative element in the center and do our electron accounting and determine exactly where the lone pairs and the bonding pairs will be around that central atom. Now, when you do that for these compounds, you get this. BRF5 will have a Lewis structure that looks just like this. SCl4's Lewis structure will look like this, and SO3 will have this Lewis structure. Now, to determine the hybridization states of the central atoms, we simply count all of the electron domains, which are lone pairs and sigma bonds. So, in the case of BRF5, we have 5 bonding pairs plus 1 lone pair for a total of 6. That means its hybridization state must be sp3d2. Right? We have to have 6 hybrid orbitals if we're going to have 6 electron domains. In the case of SCl4, the same analysis gives us 5 electron domains, or a hybridization state of sp3d on the central sulfur atom. And in the case of SO3, we have 3 electron domains. Remember, pi bonds don't count, only the sigma bonds are counted, which means we have an sp2 hybridized central atom. Now, let's ask one more question. Which of the following molecules that I'm about to show you simply cannot exist based upon what we know about the hybridization of atomic orbitals? I'll give you some choices here. BrCl5, PF6, OF4, CF4, and NH5. Now, when you do your analysis here, you have to think about the hybridization states of each of these, so hopefully you've already done that. So, if BrCl5 exists, the central atom's hybridization state must be sp3d2. In the case of PF6, it must be sp3d2. OF4 has to be sp3d. CF4 must be sp3. And NH5, if it exists, must have a central atom that's sp3d hybridized. But only 3 of these can potentially exist in nature. Because, remember, to have that dehybridization, right? To have that D subshell participating, the D subshell has to exist. So, in cases where the central atom is from the second row of the periodic table, it's simply not possible. That means that molecules like OF4 and NH5 are absolutely, unequivocally impossible to make.